show us that they have peculiar characters, behaviors that are peculiar just to them. If we study fractions and play with fractions, that is, manipulate fractions in certain selected number operations, they show us as having behaviors that they alone possess. These properties differentiate them from other forms of numbers. On our own part, we will not know these behaviors except we manipulate fractions by engaging them in number operations. Before we go into addition, subtraction, multiplication, and division involving fractions, it is important that we learn the peculiar characters that are just restricted to fractions. That takes us to lesson objective number 2, and that is characteristics of fractions. Please follow me as I develop this section. While I do it, please pay attention, because if you fail to understand this section, then all other sections hanging onto it will be difficult for you to understand. Please follow through. Now we take the characteristics of fractions. The first of the characteristics that I want to point out is this, that is number A. In every fraction, the numerator is always less than the denominator. Let us assume that in symbols, a fraction is given as x over y. If that is a fraction, that is, if x over y were to be a fraction, this statement implies that x is always less than y. And that is the message of this first property of fractions. Recall examples of fractions you have come across already. In all of them, or in each of them, the numerator, that is the number above, is always less than that is below. Let's again remind ourselves of some examples of fractions we've encountered. And here they come. We have examples here. I in 1 over 3. This 1 on top is less than this 3. If this number on top is more than this 3, we don't call it fraction. Later, in this same topic, I'll tell you what it can be called and why. Example number 2. In 2 over 5, this 2 on top, see it here, is less than this 5, which is here. So in every case of fraction, the numerator is always less than the denominator. Let us see another property of fractions. And here is the second property or characteristic of fractions. It says 2 or more fractions could have different numerators and denominators, but are equal in value. When two things are equal in value, it thinks that they have just the same use. Now, is it possible to have 2 or more fractions that have different magnitudes of numerators and denominators, and yet, when considered and compared, the fractions have the same value? Yes is the answer. Please, let us see some examples of pairs of fractions that have different values of numerators and denominators, and yet are equal in value. Please watch out. And here they come. Examples of fractions that have different numerators and denominators, and yet, when compared, they are equal in value are here. The first example is a pair of fractions which include 1 over 2 and 10 over 20. This is a fraction, and this is also a fraction. This means dividing something into 2 and picking 1. That is 1 over 2. And this means 10 over 20, meaning dividing that same thing into 20 and picking 10 from them. Dividing something into 2 and picking 1 has equal value with dividing the same thing into 20 and picking 10. Imagine breaking 1 orange into 2. You pick 1 out of the 2 portions. You keep it aside. Get the same size of orange and break it into 20 and pick 10. Compare this 10 you have picked out of 20 and this 1 you have picked out of 2. You will realize that the 2 of them are equal. If weight or mass is the way to check if they are equal, let their masses or weights be checked. You will find out that the 2 are just equal. In fact, it takes more time to divide it into 20 to pick 10 than just 2 and picking 1 out of it. What about this second example, 1 over 3 and 3 over 9? The two fractions look different, and yet they are the same in value. Break something into 3 and pick one. Try breaking the same size of that thing into 9 and pick 3 from those 9. Picking 1 out of 3 and picking 3 out of 9 are just the same. Do the comparison the same way you did in the first. You will find out that 1/3 and 3/9 have equal value. If their weight is the value you want to use, check their weights. You will see that they are just the same. Therefore, two fractions have different numerators, in this case 1 and 10, and different denominators, in this case 2 and 20, and yet are equal in value. Many other pairs of fractions behave this way. We shall see them in the course of time. Let us see another property of fractions. And here comes the third property of fractions. It says, if the numerator and denominator of one fraction are multiplied by the same number to obtain another fraction, the two fractions are the same in value. What does this mean? Please permit me to use examples to illustrate this property. Please watch out. And here come examples that will help us illustrate this statement. 2/5 is a fraction. Its numerator is 2. Its denominator is 5. Let us multiply 2 and 5 by any number of our choice. Permit me to use 3 as that number that is going to serve us as our choice. Let me multiply 2 and 5 by the same number, that is 3. See where the process is on. This 2 is still where it is. This 5 is still where it is. But both of them are now multiplied by this 3. That is 2 times 3. 5 times the same 3. That means that the numerator and denominator have been multiplied by the same number, and then the result is going to be equal to 6/15. The implication, therefore, is that this first fraction has produced another fraction. And then by this statement, we're saying that both of them are equal in value. They are the same in value, meaning that 2/5 and 6/15 are equal in value. This is a short way of writing the statement that 2/5 and 6/15 are equal in value. You say 2/5 is equal in value with 6/15. Let us see a second example. 1/3 will be treated by multiplication of both numerator and denominator to get us a new fraction. See where the process is going on. Again, permit me to use 3. That does not mean that each time you are choosing a number to multiply, that 3 is the number you must choose. This is just a coincidence. You can choose just anything depending on your objective. In this case, there was no special preference for 3. It just came to be. And now we are seeing it play out. Let us use the same 3 and multiply 1 and 3. See it going on here. 1 is still where it is. 3 is still where it is. But both of them are now multiplied by the same 3. That is 1 times 3 and then 3 times 3. If you evaluate this, you get this. That is 1 times 3 is 3. And then if you evaluate this, you get this. That is 3 times 3 is 9. We now have a new fraction born out of the first one. That means that one fraction has produced another fraction. Which is this fraction? This is one fraction producing another fraction. And what we want to highlight is, just like before, the two fractions are equal in value. That is, 1/3 is equal in value with 3/9. In symbols, we can summarize this property. Let's see how it is done. And here comes the summary. The summary says, A/B is equal in value to AC/BC. AC means A times C, and BC means B times C. Don't forget that what took place in both cases was multiplications. Likewise, this is how we summarize multiplication in this case. AC means A times C, and BC means B times C. Notice that the same C has been chosen to multiply both numerator and denominator to get us a new fraction that may look different but has equal value with the first one that gave birth to it in the first place. At this point, let us move to another property, another feature of fractions.
And here comes the fourth property of fractions. It says, if the numerator and denominator of one fraction are divided by the same number to produce another fraction, the two fractions are the same in value. Like before, please allow me to use examples to illustrate this property. Please cooperate. Now, here are the examples. Just two examples. The first example is 12 over 20. 12 is numerator, 20 is denominator. I want to divide each of them by the same number. That is, divide 12 and 20 by the same number. I have chosen 4 to divide both of them with. That is, to divide 12 by 4 and divide 20 by 4. So that both numerator and denominator, meaning 12 and 20, are to be divided by the same number. The same number here is that 4. Let's see the result. When 4 divides 12, the result is 3. When 4 divides 20, the result is 5. What it means is that the first fraction has produced another fraction. 12 over 20 has produced 3 over 5. The implication from this statement is that both fractions now have equal value. That is, 12 over 20 is equal in value with 3 over 5. Don't forget how this became this. Just by dividing 12 and 20 by a chosen number, that is 4, this 3 over 5 came to be. That does not mean that at all times we must choose a whole number like this to divide the two numbers with. It is just for convenience that we chose 4, a whole number that will divide 12 and 20. It could be 2, it could be 3, it could be anything else, not even a whole number. We can even choose 1.5 to divide 12 and 20 with, depending on our objective. At this point, there is no objective that is being pursued except to show that when the numerator and the denominator are divided by the same number, that a new fraction is going to be produced, and that new fraction has the same value with the first that gave birth to it. The same thing is what has happened to this one example here. We have 5 over 15. Let us divide this 5 and this 15 by a chosen number. Permit me to choose 5 to divide both of them with. When 5 divides this 5, we have this 1. When 5 divides 15, we have this 3. That means that this fraction has produced this fraction, and 2 of them are equal in value. That is to say that this 5 over 15 is equal in value with this 1 over 3. Let us, like before, provide the summary in symbols of this characteristic. And here is the summary. A fraction, any fraction, a over b, is equal in value with another fraction produced by it by means of division by the same number c. That is, a over b is equal in value with a over c over b over c. We still have more properties of fractions. Please, let us see. And this is the fifth property of fractions. The thing says, the value of power of fraction remains the same when evaluated with separate powers of the numerator and denominator. Again, please permit me to use examples to illustrate this characteristic of fraction. Here are the examples. Example 1 goes this way: 3 over 5, together all to power 2. That is, we are looking for the power of a fraction. This is power 2 of this fraction. And so we are simply saying that the value we're going to get from this is the same thing if we separate this 3 and this 5 and still get their powers. This is the implication of this statement in connection with this example. Now let's proceed. To get it clearly, recall that if something is raised to the power 2, it simply means let that thing multiply itself and appear 2 times in the process. 3 over 5 raised to the power 2 means let 3 over 5 multiply itself, and when multiplying itself, let 3 over 5 appear 2 times. See it happening here. 3 over 5 times 3 over 5. 3 over 5 has multiplied itself. It has just appeared 2 times in the process to fulfill this command. And so this is a fulfillment of this, obedience to this command. Now let us evaluate 3 over 5 times 3 over 5. Now, 3 times 3 will give us 9. 5 times 5 will give us 25. Please, be patient. Later in this same topic of fractions, you will learn how this and this became this over this. That is how 3 over 5 times 3 over 5 became 9 over 25. Because in the meantime, it is assumed that you don't know yet how to multiply fractions, and I'm here applying it. Please, until then, just know that this times this is equal to this. 9 over 25 is the same thing as this. If we express 9 in index form using 3 as a base, 9 is the same thing as 3 to the power 2. 3 to the power 2 means 3 times 3. Also, if we express 25 in index form using 5, what we have is 5 raised to the power 2. That is 5 to the power 2 means 5 times 5. It therefore means that a different way of writing 9 over 25 is 3 to the power 2 over 5 to the power 2. The implication, therefore, is that this expression has become this expression. Then the summary is that 3 over 5 all to the power 2 is equal to 3 separately to the power 2 over 5 separately to the power 2. Therefore, fulfilling the obligation expressed in this property, a power of one fraction, power of a whole fraction, can be evaluated by evaluating the powers of the separate numerators and denominators. Please, again, check how this became this, and come here to summarize the process. Let us do likewise to example number 2. We have 1 over 2 all to the power 3. What does this mean? It means let whatever is in this bracket keep multiplying itself and appear 3 times in the process of multiplying itself. Therefore, how many times will this 1 over 2 multiply itself? 3 times. Please see it happen here. 1 over 2 times 1 over 2 times 1 over 2. That means that this 1 over 2 has appeared 3 times in the process of multiplying itself. And next, just like this became this, 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. That means that the result of this is equal to 1 over 8. We can express this 1 over 8 differently. How? 1 is the same thing as 1 to the power 3. 1 to the power 3 does not mean 1 times 3. It means 1 times 1 times 1. It means let 1 keep multiplying itself until 1 appears 3 times in the process. Also, 8 can be expressed in index form using base 2. When that is done, we have that 8 is equal to 2 to the power 3. Now, we see that the summary is that this, having become this, is written that 1 over 2 to the power 3 is equal to 1 to the power 3 over 2 to the power 3. That means that power of a fraction has been evaluated with separate powers of the numerator and denominator. That means before, this fraction was together, that is, numerator and denominator were together raised to the power 3. But now, we have them separated. This 1 to the power 3 over 2 to the power 3. This is correct mathematically, and you can test it out in real life. You can choose more examples for yourself, and then in the end, you will see that the results are the same. All right, at this point, let us offer a summary of this process. Please watch out. And here is the summary. A over B, that is any fraction, raised to the power anything at all, is equal to A to the power n over B to the power n. You will still meet this type of expression in a topic known as laws of indices. Until then, just know as a preview that this is valid. Let us see the final property of fractions as chosen here for discussion. And here comes the 6th and the final property of fractions as chosen in this topic. It says the value of roots of a fraction remains the same when evaluated with separate roots of the numerator and denominator. In fact, we ought not waste time in this. The reason is that this word root is also a power. Each time you hear root, it means power that is written as a fraction. For instance, if you write 2 raised to the power 1 over 2, it simply means square root of 2. So when you hear root, take it to be power of a fraction. That is, fractions serving as a power to a number. Because root is just a different meaning of power, I would not repeat, given the examples that are going to highlight the application or the understanding of this statement. I'll just proceed to writing the summary of the process. Let us see. Now find the summary. It says the nth root of a fraction, which is a over b, is the same thing as the nth root of the numerator over the nth root of the denominator. Like I said earlier, watch this note here. Nth root of a is just a different way of writing a raised to the power 1 over n. That is nth root of a. Assuming 2 is here, we will be calling it the square root of a. If 3 is what is here, we will call it the cube root of a. If 4 is what is in this place where n is written, then we're going to be calling it the fourth root. If 5 is what is there in place of n, we'll be calling it fifth root of a, and so on in that manner. Therefore, this symbol is just a symbol invented to differentiate powers which exist as fractions from powers which exist as whole numbers. Before, we just used only n as the power, and that n was supposedly a whole number. Whenever a power is a fraction, we stress it by using this symbol. And that symbol is called the root. The type of root depends on what is here. Like I said earlier, if it is 2, we call it square root. If it is 3, we call it the cube root in that manner. So this is just another way of writing this expression. Because of that, all examples given in the most recent property of fraction apply here also. At this point, let us see whether we can tackle some challenges herefrom. And here comes the checkpoint. It says, number 1, from each of the following fractions, obtain another fraction equal in value using multiplication. I just hope you know what I mean by this. Number A, 4 over 5. B, 5 over 9. C, 2 over 3. Number D, 4 over 15. In this case, it says another fraction, not two fractions. So you can choose any constant to multiply the numerator and denominator. This is just meant for practice. No value, no constant has been suggested. Suggest anyone and use it. Number 2, from each of the following fractions, obtain another one equal in value via division. I just hope you remember. Okay, assuming you to, please look at the fractions. Number A, 20 over 30. B, 16 over 24. C, 30 over 45. Then D, 15 over 48.